Okay, so anyway, what we were talking about last time was we sort of introduced formally file systems, or I probably shouldn't say formally, right? Because it's an engineering thing, right? But the idea of having files and directories and addressable through paths and so forth. And we left off talking about how to manage file contents. How do we actually allocate regions of disk space to this thing called a file? And we had talked about all of these different ones, and we started talking about index allocation. We kind of got through it, but we stopped in the middle of a kind of important topic, so I wanted to go back to it. The main issue that we have to think about when we're designing file systems is there tends to be two patterns of access. One is sequential, where I start at a particular location and scan, typically from the beginning of the file, and scan through sequentially, and the other one is I have an offset from the start of the file. So it's a logical offset, and I want to go to that specific position. And obviously that correlates to some disk block on the disk device itself. So we have to think about performance. We have to think about susceptibility to various kinds of fragmentation. Obviously, if the device is a device that can have data fragmentation, but these are sort of the issues that we can run into. And so we had picked up with indexed allocation, which basically used the same idea as linked allocation and also had similarities with the file allocation table, except it was kind of a per file allocation table. So one block of the file's data, if you will, is allocated to recording what other blocks are actually part of the file in sequence so that we know what sequence to access the blocks. And so those become an index block, aka an inode, that describes the contents of the file, or at least where it resides. Okay? And we talked about this in some detail, that this allows us to do both direct and sequential access quickly because we can just load the index block into memory and then use it. And keeping it in a cache or keeping it in a buffer, we can do lookups against the file relatively easily. I think we talked about this, so I'll go a little bit further. The neat thing is using this node for storing data, metadata, because if we use it for metadata, then that means that it becomes really easy to have hard links in our file system. And part of the reason why other file system data structures can't really do hard links is because they don't have enough information associated with the file itself. Okay? And so that's kind of a big issue that you run into with those file systems that don't support that. Okay, so anyway, we talked about that stuff. Now, where we were sort of starting to run out of time was this whole question of how do you deal with the needs of small files versus the needs of large files. And I would have to say that the previous approaches up until relatively recently have been kind of ad hoc. And so this is an area that I definitely want to dig more into to try to understand the rationale behind some of the older approaches. But we're going to talk about them because they're suggested in the Pintos Homework 6. And so I want to talk about them. But the idea here is that you don't want small files wasting space with an index that's really empty. So let's say, for example, instead of allocating one index block, we allocate 16 index blocks. Okay. Well, if I have small files, and you tend to have a lot of small files on a file system, then that's wasting a lot of a large index in those kinds of situations. But what about large files? Okay. Well, if we have an index block, and then maybe when we run out of space, we overflow to a second index block, and then we overflow to a third index block, and so forth. Well, now we've got this linked list we've got to walk down just to figure out how to access a particular offset. So accessing high offsets in a sequence of linked indexes doesn't work very well for large files. So how do you balance the considerations for both of these? That's kind of the issue that we have to figure out. Okay? So one option is a linked sequence of index blocks. It's not great. It does okay. But each index block would have basically just the sequence of block numbers that comprise that file. Just like a single index block would be, you just devote a little bit at the end of each index block to chain to the next one. Okay? So either you say this is the end of the index, or you have a pointer to another block. Now, this is not bad for small files. I was just talking about this. The big issue is when you want to access directly positions that are far along in a large file, and you have to chase through this chain of index blocks. If you're doing sequential access, that's okay, because as you're doing sequential access, you can just, again, keep buffered the current index block you care about, and just keep walking through them, and so that's okay. But it's really when you want to do direct access toward the end of large files. So let's say you're appending on a large file or something like that. That's going to be a really expensive operation here. Here's some math just to show you some examples. Storage blocks of 512 bytes. And let's say you have 32-bit entries, so this is definitely a 32-bit kind of approach. So 512 bytes divided by 32-bit entries gives you 128 entries. And so let's say you have 100 or so entries, because you also need space for metadata, then you can access up to about 50 kilobytes with one index block. Okay, that sucks, right? Everybody is like, okay, I definitely would love to have... I mean, people take photos now that are megabytes, so why would I worry about, or why would I necessarily be excited about supporting 50 kilobyte files? Sucks for another reason. We like virtual memory now. Everybody loves virtual memory, I hope by now. But anyway, virtual memory is frequently leveraged heavily by the operating system to do file I/O. And if that's the case, then 512-byte sectors doesn't make a lot of sense for the unit of data that I move back and forth from the file system. So a lot of times we use virtual memory pages instead. Okay? And so you have 4 kilobyte pages. You know, yes, it's multiple sectors. It's 8 sectors, but and that affects atomicity of your interactions with the disk platter. But hey, you know, there's worse things in life. So you have index entries referring to 4 kilobyte blocks instead of referring to 512 byte sectors. Well, now I can access a file size that's kind of useful, 4 megabytes or 4 megabytes, if you will. So we're starting to talk about something that's moderately usable. Okay, and so this is sort of the way that people would reason about these things. Second option is a multi-level index structure. This is where everybody is moved. This is the direction that everybody's moved. And it's been that way for quite a while, but I'll point out the thing that makes me confused in a moment. But the idea is that you can have index pages that refer to either blocks or other index pages or some combination depending on the needs. Okay? So you have this approach. And so the idea is that maybe you can increase the depth of your indexing structure as the size of your file grows. Okay? And so then all you have to do is navigate your index structure to figure out how to map a particular logical offset to the block on disk that it actually occupies. And by traversing this index, you can do sequential access. Okay? And so this should scale much better with large files. Okay, so we say that a single level index can index up to a 4 megabyte file. So again, we're assuming 4 kilobyte blocks, 32-bit entries, blah, blah, blah. I mean, nowadays we don't do this because we want to be able to So again, some of you may have encountered this. It's unlikely, but you may have encountered that on 32-bit Linux, it was common for 4 gigs to be a file size limit. And then you could actually compile Unix programs with particular switches to get you larger files. And so that would allow you to be able to do a little bit more. But nowadays, when everybody's on 64-bit, 4 gigs is kind of like, why is that a limit? You know? So we can work with much larger files now. So let's say you want to go above 4 megs. Well, then that's going to require 2 indexes. Now, this is where you have an interesting question, because 2 index nodes chained together isn't that big a deal. I mean, what does it matter if one is first and the second is second, or one is a parent and another is a child? That really is irrelevant at that level. But if we need to start getting bigger, then we can start thinking about more sophistication with how we chain these things together. So like it says here, a simple 2-level index would buy you already a whole bunch. So leaf pages would each index up to 4 megabytes of the file, and then each entry in the root. Okay, well, each entry in the root corresponds to a whole leaf in the index, and so that corresponds to 4 megabytes of the file. So you could use 2 levels to index up to 4 gigs. That seems pretty cool. 3-level index, now you can get up to 4 terabytes and so forth. So you can see that because these index nodes have such a broad, how should I say it? I mean, there's several ways that it's described. One is to have a high branching factor. So every node can access a whole bunch of children. Because of that, you can have a very shallow index and index a very large data file. So that's pretty promising. Okay. So that's neat. Now the third option, and this is where I'm confused, is basically blending these different approaches in various ways. Like, from what I understand, NTFS uses straight-up B trees. I don't. You guys familiar with B trees? You're familiar with B trees, and you guys have. If you take 122, you'll definitely learn about B trees because it's a database implementation class. But the idea behind a B tree is just like that multi-level index thing. I have nodes that have a very large branching factor, so anywhere from 300 up to 1,000 sometimes, if you're lucky. But anyway, you have a very shallow, broad tree is the idea. And the cost of access is basically proportional to the depth of the tree, not its breadth. And so very effective. And NTFS uses this. Many modern file systems are now using B-tree type data structures for doing indexing into large data files. It works really well. It works for small files. It works for big files. So I don't see necessarily what the motivation is for this, but I want to go read about this. ext2 has these weird nodes. Okay? And again, the Pintos write-up suggests that you implement something like this. So you have file metadata as part of that inode that describes the file. And then you have some number of pointers to either indexes or to data blocks. Okay? And so like I say here, the root index holds 12 pointers to 12 disk blocks. And so the idea being that this is going to allow you to access tiny files very efficiently because you're already going to have the file metadata in memory. Okay? And they're called direct blocks. Then if you overflow that, so again, you have to do this careful math to say, okay, I've overflowed the first 12 blocks. Then you have more entries for single indirect blocks. And you'll notice that that entry points to another index page, and each index page points to data blocks. So a single indirect node will get you up to 4 megs or something like that. Okay? So that's single indirect blocks. If that becomes insufficient, then you overflow into double indirect blocks. Okay? And so this is going to get you a lot further because now you have 2 levels of indexing before you get to your data nodes. And that will allow you to access much larger files. And then if you're really crazy, then you can even have triple indirect blocks. Okay? And basically in combination between this approach and extents, because ext, I don't remember if ext2 does. Well, maybe it does. But I know that ext3 does and ext4 as well. Supports extents on top of this, then you can get into extremely large data files. Okay. So with the Pintos implementation, they don't want you to use triple indirect blocks because you only need to support up to 8 megabyte files. And so I think you can get away with a one single indirect, one double indirect, and then you basically cover the needs for the assignment. Okay. But this is what ext2 does. Okay, so that's the idea behind some of these weird hybrid approaches. Now, the question that I have, which is what I was telling you before, is I don't see a benefit of this over B trees. and so that's where I'd be interested in go looking. But honestly, ext2 and ext2 has been deprecated for quite a while, but I mean we're up to ext4. I think I've seen a lot of systems moving away from ext4, so I'm not sure this is necessarily catching on any longer. Does anybody know about this stuff? Anybody do any reading about like Linux file systems or anything like that? Like we just got this big giant NAS at home. It's a network attached storage device. And when you set it up, they immediately install BetterFS. Like they don't even use an ext file system for managing the disks. And that's for various reasons, but we'll talk about that when we talk about journaling, because from what I understand, BetterFS is journal. Do you have a comment?
Or question?
Yeah.
So there's some file systems out now that, I mean, they're described as file systems. They are kind of file systems, but they incorporate things like like creating a file system that is actually on multiple computers or is.
Oh, okay, like a distributed file system, basically. Yeah.
There was one we were messing with called ExtremeFS.
Okay.
Kind of worked.
Yeah.
It didn't. Are those still file systems in this sense? Or?
Yeah, they are definitely file systems in the same sense, but they just have a much more complicated problem to solve. I mean, there's several things that you try to solve with a distributed file system. One is increased reliability, so that if some node explodes or whatever, that you don't lose data. And so that's one big motivation for that. And another big motivation is moving data closer to the people who need it so that they can access it more quickly. And so those are sort of the two big reasons why you would see a distributed file system. The other thing that you see a lot is things like NFS. You probably have heard of NFS. I think it actually stands for Networked File System. And that's historically been really important for computing clusters, like when UGCS was a place where people would go and sit down and work, and the CS lab, yeah, where people still go sit down and work. You log into one computer, you use the the stuff in your home directory, and you finish up, and then you go sit down at another computer, and you log in, and all your files are still accessible and everything like that. So it's interesting because those are kind of different solutions to the same problem. Like a network file system basically turns disk reads, air quotes of course, into network interactions. And it tries to provide all the same kinds of guarantees that you might have from a file system. Like if I sync, do I know that that data got saved somewhere persistently before the sync comes back saying yes, and so forth. And then when you have distributed file systems, making a distinction between networked and distributed file systems. Distributed file systems may save the data locally, and so some of your reads and writes will just be reads and writes, and some will be network operations. But then there will be additional mechanisms in place to support failure of nodes in the system. Partitioning, I don't know if you guys have heard about partitioning of a network of computers. If you divide it into two separate networks and they're now divided, now you have a consistency issue that can start to emerge between those partition networks. So you have all kinds of infrastructure that starts to be created to handle those kinds of problems. So it's basically taking the file system problem and making it harder. But sometimes what people will do is they'll try to build a distributed file system that uses a local file system as a basis so that they don't have to solve these kinds of problems of how we lay out data and how we access it and make it efficient for large files. They just focus on the networking issues, and then you can use whatever lower level file system you want locally. So yeah, it's a really interesting topic. I remember some students from 4 or 5 years ago actually wrote a distributed file system for a class. I don't know if it ever got very far, but I don't know if I think it's on Linux. I know it's on the Mac, but there's actually a layer called Fuse, which allows you to do user space file system implementation. And so I think they actually used Fuse to write a user space distributed file system implementation for a class. So It was pretty cool. Yeah. Any other questions? I don't want to get too distracted because there is stuff to talk about. Some of it you've already seen, some of it you haven't. But I did want to make sure to talk about that because that's going to be relevant to the last assignment on Pintos. Okay, so we've got processes. They interact with files. We talked about this in the first week, so that's all stuff that you've seen before. But when it comes to interacting with the disk, that is like one of the slowest things that the computer can interact with. The even slower thing is the user, but the disk is pretty slow, and so the OS tries to minimize the amount of interactions with the device itself. And so what it does is it keeps a buffer, and that buffer allows it to serve some disk requests, reads and writes, against memory, DRAM, as opposed to actually talking to the disk itself. And so that's cool, except the problem is this is a shared cache that is used from multiple processes. Okay? And so this is where the OS has to be careful about how to manage these kinds of interactions. Okay? We have reads and writes that can be performed on the same file. The question is, how do you handle it? Well, most of the time the OS isn't really required to have rigorous answers to that question. It can actually take some shortcuts if it really needs to. Okay? So for example, it doesn't have to maintain the same consistency guarantees that databases do. Databases have a really strict set of requirements, but as long as the OS provides some basic requirements, then databases and other kinds of systems can be built relatively easily. Okay, yeah, standard APIs can manage these interactions. Basically, if you have reads, nobody cares. Reads basically never interfere with each other, even when they're overlapping. It's like nobody really cares about that part. Now, if you have a read happening after a write, you would like the read to reflect the write. Okay? That just makes sense because if you're doing all this against a cache, and then the cache is being used on the to eventually write back to the device, then the cache should reflect the write, and so a read should hit that same part of the cache, and you should see the results of the write. So that's the idea there. Let me actually say one other thing about this, is that there may be some unit of writing that's actually imposed. So you say, I'm going to do 4K pages or something like that. A write to a page, and then the read sees that write to the page. Okay? You don't want to see really nasty stuff of like a buffer being torn between two different operations, where part of the write is completed, part of the read is occurred. It can get really nasty then. Okay, writers sometimes block each other depending on how the OS wants to handle it. And this also depends on writing to a particular section, like are the writes overlapping or non-overlapping. If they're not overlapping, who cares? Again, they can proceed without any problem. But if the writes are to overlapping regions, then you may want to prevent that kind of thing happening. Okay. Now here's the part that really is important. And it's the part that touches data and metadata. Because remember, the file system, the operating system kind of doesn't care what applications do with files. It's like you can store whatever you want. You can interact with them however you want. But now we're starting to talk about the viability of the file system itself. We have to allow file appending to be correct in the context of multiple concurrent appends. And the reason why this is important is that you're extending the file, so you're modifying the metadata of the file, and then you're going and writing data into the file itself. Okay? So we have to make sure that this is done correctly to avoid corruption of metadata. That's like the big reason why file systems care about this. Okay? There's a few other things that are important, like being able to write logs to a log file. Obviously, OSs need to be able to log things to remember what happened if stuff explodes. So being able to do that effectively is also a good idea. But the main thing is that the OS needs to protect the correctness of the file system. And since we're manipulating metadata, that becomes pretty important. Okay, so how do we manage this stuff? I'm just going to give you a few details about APIs that are exposed by various operating systems. Windows has a create file call that you can use to lock a file when you open it or create it. And that way you can prevent other processes from actually doing anything to it. It's kind of interesting because this is forced. It's not, how do you say, well, there's another approach called advisory. Oh yeah, I suppose the words are advisory versus mandatory. But in this case, basically, Windows will disallow operations on that file by other processes. It will prevent those things from occurring. Okay? Now, advisory locking is a lot weaker. Advisory locking means if you choose to participate in the locking mechanism, then the OS will tell you when somebody else has a conflicting lock going. But you're not required to use the advisory locking mechanism. You could just go do the file I/O and it would always happen. So the OS isn't preventing you. So it's not mandatory, it's just advisory. You'd like people to play along well. The way I think of it is like acquiring locks in a concurrent program. Nobody requires you to acquire the locks to do your thing, but acquiring them will make things work. Okay, so a couple of examples of this. You have flock. Okay, so that'll acquire and release advisory locks on an entire file. So other processes using flock will see your advisory locks. Processes that don't care and just access files will just access the file. Okay, so nothing will prevent it. Okay. Now flock is reasonable name, right? Flock seems like a reasonable name for locking a file. Well, there's also lockf, and it's a little bit annoying. But lockf is for locks on regions of files as opposed to the entire file. Okay, see, this is really clear. But anyway, you can see that it talks about doing it in a shared versus an exclusive mode. These are basically just wrappers to this really sophisticated function called fcontrol. And I'm pretty sure fcontrol is a system call because everything it can do is all syscall kind of stuff. So, for example, duplicating a file descriptor or assigning a new value to a file descriptor. Those kinds of operations are fcontrol issues. Being able to turn on and off special modes for file descriptors, like turning on non-blocking mode for a file descriptor, that's something you do through fcontrol. And also this advisory lock stuff is done through fcontrol. How's my duplicate, set control flags, I/O signals for open files, acquiring So basically, you see all the kinds of things you can do through fcontrol. So lockf and flock are just wrappers for specific operations. Okay. Now there are mandatory locking operations for some operating. Again, it really comes down to what the OS decides it wants to provide. Linux has mandatory file locking, but it's not required. It's not spec'd. So you can use it, but then you're tying yourself to Linux. Or if you want to be multi-platform, then you'll have to provide an abstraction around it. That also works. There's been plenty of times where I've had to write software that had to run on Windows and Linux, and you just you write wrappers for the stuff that's OS specific, and then you just run against your wrappers. That's not the worst. Okay, any questions about this? So this is the kind of thing you'll have to think about for Pintos. Pintos really has pretty limited requirements as far as reading and writing concurrently. Writes shouldn't interfere with writes, and when units of buffers, I can't remember the size of the buffer, I can't remember if it's 512 bytes or 4 kilobytes, but a single buffer, like a write operation, should finish before a subsequent read to that buffer commences. So those are kind of the things that you need to think about. Appending definitely needs to be atomic. That's just a universal kind of requirement for file systems. All right. Let's see. File deletion. So we're going to start to talk about a slightly different topic. Does anybody have any question about locks before we move on? Okay. So deletion is interesting. Okay? And I want you to notice something about deletion, which I think is kind of fun and scary. Obviously, the details depend on the file system format, but we need somehow to record when space is available for new files to utilize. Okay, so here's the process. Let's say that we're deleting home/user1/b/a. Okay, well, we have to find the directory entry referencing that data, and we need to get rid of the directory entry. If we've hit 0 links to the file data, then it's time to reclaim the file data as well. Okay? So how do we actually reclaim that data? Well, all we really do is somewhere say those blocks are now available for other people to use. Okay? So we have this requirement that we need some way of tracking free space, and there's various ways it's described. A lot of times I've seen it called a free space map. Free space list is one kind of lame way to record it, but one can certainly do it that way. Okay. So just as a simple example, you remember the file allocation table format, where you have that table, and each block says, here's the next block in the file that I'm in. So everything is recorded in one table, and some of the entries will have a value saying, I'm available. And so the file allocation table actually already encodes its free space map as part of the FAT format. That's one of the neat things about it, is that it overlaps all of these different uses in one table. But it's common to see file systems use bitmaps. Okay, bitmaps are great for this kind of thing. You just have a 0 for, what do I have here? 0 is unavailable, and 1 is available. And so if you need to find a free block, you just go look for the first 1 bit that you need. If you need a chunk of available blocks, then you look for a run of 1 bits. So this allows you to search through the free space map relatively easily. Okay. Let's see. Yeah. So like I said, you can make it more efficient. There's a whole bunch of clever tricks you can do to make this pretty efficient. So we're not going to spend very much time talking about that, but you can imagine the kinds of tricks you would play to, let's say that you want a chunk of like 12 blocks. Then you could probably figure out some clever things to do to make that happen quickly. Okay, so bitmap takes up space. No big surprise, right? Nobody, there's no such thing as a free lunch. So 4 kilobyte block, well, how many bits does that have? It has 32,768 blocks. So you could use that to record a free space map for 128 megabytes. That's not bad, okay? We all know that we lose a lot more space to formatting disks. I mean, I love it when people who don't know very much about computers, they get a brand new disk. I used to see this a lot. I think people know about this more now. But they, back when disks were getting larger and larger, I got a 5 gig disks and I formatted it, and now Windows says I have like 4.2 gigs. Where'd the rest of that go? Well, there's stuff that the OS needs to use to keep track of things. That may be extreme as far as data loss, but you get the idea. Some of it has to be used for things. Okay? 1 terabyte disk, that would require 8K blocks, okay, to record the free space if it was using a bitmap. Okay, so that's not horrible. And so there's various ways it can be laid out. I always get scared when people lay out stuff all in one place, because you're kind of presuming that the device is not going to fail in some weird way where part of it is available and part of it is not. And one of the interesting characteristics of ext2 and ext3 and ext4 is that it basically divides the disk area into groups, large chunks of space, and each group has this requirement that it has a bitmap at the beginning of it that can fit in one block, and that describes the available space in the group. Okay? And then the groups are all managed in some mechanism. Okay? So this basically, you can see that the free space bitmap can be structured in a lot of different ways depending on the needs of the system. Okay. Now another one is an actual list, and again, this is where probably a bad idea, because how would you get a whole sequence of contiguous blocks using this approach? Okay, so I have a linked list of free blocks. The file system just remembers the first block in the free list, and each block says this is the next block in the free list. Okay, well, someone could do that. It's easy to find an available block, but finding a run of contiguous blocks is difficult. Okay. And so this does tend to be more I/O costly and tends to lead to a less effective management of disk space. Okay. So that's not great. The other thing that you notice really quickly is, yes, these blocks are all available, but it's lots of I/O to chase things down, because I have all this free space in each available block, and I'm not using that space in any useful way. So a lot of times when people want to have lists of blocks, each block will actually store as many free blocks as it possibly can. It will record the indexes of all of the free blocks that can fit into that block, and then at the end will be a link to the next free block that stores a list of free blocks. Okay? So you could do something like this. Now again, if somebody wanted to use the free block that had a list of free blocks in it, well, you either have to relocate that data or you need to make sure that that one's not going to be used very quickly. Because if you were to use that free block, you'd have to evacuate that data somewhere so you don't forget it. That would be really bad. Okay. So anyway, this is an interesting approach, but I think bitmaps make a lot more sense. And I think most people who look at these kinds of things tend to agree that bitmaps make this stuff a lot easier. Okay, any questions? One of the things about these kinds of systems, you kind of notice that the more practical and the less theoretical, the more possible answers you have to how to do things. And you definitely see that with file systems. All right, let's see. Other ways of recording free space? Sure, you could do all kinds of fun things. Now, here's the thing that I want you to notice. You delete a file. You remove the directory entry. You go touch a free space map. Okay. Both of these steps do not require you actually touching the file data itself. Okay? And that's one of the things that you notice is that when you delete a file, oftentimes the file's data sticks around. Okay? I have a feeling that probably all of you are generally familiar with this concept. You delete a file, but its contents aren't fully destroyed. And so we call this data remnants. Okay? That the data remains on the platter. At least some of it does. You truncate a file, it definitely is going to remain somewhere. The file system will eventually reuse it, but it's still available somewhere. Okay? So this is good and bad in a number of ways. This used to be really popular in the DOS days because the DOS way of deleting a file was very reversible. And so there were quite a few times where people would delete things and then go and try to undelete the file and have success. Nowadays, it's a lot harder just because of the way that disks are managed. So that's cool. If you accidentally deleted that important spreadsheet, you can go get it back. Delete all the photos of your ex. Like, oh, and then we got back together. I better get those photos back. But another one is if you have somebody who's being naughty and they're using a computer to track their massive crime empire or something like that, then it's nice because even if they wipe the computer, you may be able to go and retrieve information from it. So that's kind of nice. Of course, the way to get around this is not unknown, right? Everybody generally understands that regardless of the type of device, there are ways of securely erasing them. For hard disks, it tends to be overwrite the sectors multiple times with various patterns, and then it's basically impossible. And of course, you can always take a hammer to it or something like that if you have the time, or some kind of magnetic circumstances. Well, there's a lot of ways of erasing those. And then solid-state drives are similar. There's ways of securely erasing solid-state drives. Okay. So this is an interesting thing. Yes, question?
Why does it take more than one overwrite pass? Like, why couldn't you just write 0 to the entire hard drive?
When you write zeros, and this is all speculative, I don't actually know of any stories where people have taken a device and restored overwritten data that was just overwritten once. But the idea is that when you write a 0 to a location that used to have a 1, then you don't fully reset the magnetic field of that place to 0, or what is equivalent to 0. There's still some, again using this term, remnants of the 1 bit that was there. And a sophisticated enough attacker would be able to identify that. So maybe they could retrieve some of the information from the device. The idea of writing multiple times and writing specific like 1s and then 0s and then 1s or whatever is that that should introduce enough random noise that you can't actually go and extract. The whole fundamental premise is that a write of a 1 or a 0 is not a total, complete changing of the state of that physics. And so when you read it, what you're really reading is it mostly 1 or is it mostly 0, and that kind of stuff. There is a guideline, like the U.S. government has a guideline as to how many times you should overwrite data before it's considered erased. And I'm presuming that's because there's been like stuff that you would see in action movies that happens in real life that would indicate that writing this many times is good and not that many times is not good enough. But I just don't know. Like I said, I haven't heard any stories about data disk restoration things. Should be interesting. It'd be really interesting for sure. Any other questions? Okay, solid state. This is the last thing I want to talk about with file systems because this is kind of an important thing. Some of this information is from CS24 as well, so there is some overlap, but I just want to talk about this because there's a point. There's actually a really important point at the end. Solid-state drives are annoying because, yes, you can read and write blocks, 4 kilobyte blocks, 512 byte blocks, but they have these weird rules. It's these strange rules about how you can interact with them. You're only allowed to write to empty blocks, okay? And therefore, when you want to perform a write, you need to make sure that you have an empty block, or if you don't, then you need to erase stuff. Well, there's a second problem, which is that blocks can only be erased in large groups, not individually. So while you might be able to read 4 kilobytes, you might only be able to erase 2 megabytes at a time. And so obviously there may be some blocks in there that have data, there may be some blocks that don't, but you can erase a big giant chunk at once. Okay? So this is the challenge with solid-state drives. And so if there's empty blocks on the SSD, then you can perform a write immediately. But if there are no empty blocks, or if you're getting dangerously low, because of course computers like to preempt these kinds of issues, then you have to start erasing things. You have to start reclaiming some of those written blocks so that you can then make them available for subsequent writes. Okay? And of course there's the whole issue that only so many erase cycles are allowed before the cell may no longer be able to hold information effectively. Okay, so that's another side thing. We're not talking about wear leveling in this lecture. Okay, so we have a flash translation layer. Okay, that receives logical block addresses. So I want to access block 0. I want to access block 493. Flash translation layer says this is stored in this cell. Okay. And you'll notice the way that I have this in the picture, F1.1, 1.2, 1.3. So block 1, block 2, block 3 of file 1, and so forth. Okay. Now here's the thing. You write a file. In this case, let me see. Yeah, so block 2 of F1 is written. You're writing your Pintos thingy. You hit Command S or Control S because you like to save a lot so you don't lose your work. And so block 2 in file F1 is written, and what happens is it actually marks that cell as old and then stores that thing in a new block. So notice F1.2 prime. Now it's the solid-state drive that's doing this. It's not the OS. The solid-state drive sees, oh, you've got another write to that logical block. So I am going to perform that write over here in this empty cell. I'll mark the old version of that logical block as old and update the flash translation layer to say now it's living over here. Okay? These are the steps that the solid-state drive is carrying out because it can only write to empty cells. Okay? So over time we end up with lots of old things. And so the SSD has to start erasing blocks to free up space. Okay? Now obviously we have an example here where an entire erase block can be freed. I mean, we have a nice simple SSD with only 4 write blocks or 4 memory cells in an erase block, so we just blow that one away and we're happy. Okay. We have a bunch of free cells, and so it can carry on. Now, if we have a situation where we are getting concerned and we want to preemptively reclaim some memory cells, then we may have an erase block that still holds data. And remember that if an erase block is 2 megs, then it's pretty likely we're going to have erase blocks with data in them. So let's say that we want to erase this guy. So 2 cells marked old and 2 that are not. Okay. Notice we have 3 available cells right now. So if we do this, the first thing that we have to do is to relocate these still in use cells to other cells. Okay? And then we can go ahead and erase that block. Okay? The reason I pointed out that we had 3 available cells is that now we have 5. So we are making progress. But you'll see that we have this issue that we have to do relocation sometimes. And so this is actually gives rise to this phenomenon called write amplification, where you write to the SSD, and it says, man, I got to make up some more space. And so it starts moving things around. And so you start getting writes within the SSD to handle a write to the SSD. Okay? And this dramatically slows down the performance of the solid-state drive. So let's close this circle here and illustrate why this becomes an issue. So this is a little bit about wear leveling. But here's the question. How does the SSD know that a cell's contents can be marked old? So far, with everything that I've described here, the only way that we know a cell can now be marked old is when somebody performs a new write to that logical block. That's the only thing the solid-state drive sees that says, oh, hey, I can write this other one to be old now. Okay. So that's kind of an important issue. Now think about this in the context of deleting files. We have file data in the SSD, and then we delete it. Well, we don't really touch the file data. We touch other things. We touch directory entries. We touch free space maps. We don't touch the blocks themselves. Not that we want to touch the blocks, because, I mean, why write to them? We don't need to write to them. Okay? So, basically, the OS is trying to be efficient and touch the device as little as possible because it's slow. But, yeah, so like I said here, the file F3 is deleted from the solid-state drive. Basically, the solid-state drive only sees directory entries modified. It sees the free map modified, but it doesn't see anything really about file F3 that's modified. And so it doesn't know that it needs to, or that it can discard those blocks. And this is the big issue. If it were to erase, now we have the second bank. If it decided to erase the second bank, it would still be saving those blocks that were part of file 3, even though the OS doesn't care anymore. And this is a problem. This was one of the biggest performance issues that emerged when solid-state drives started to be widely used. And so this is where trim came into the picture. Okay, how many have heard of trim? Probably all of you have seen trim at one time or another. Trim is the solution to this problem. Trim basically allows the file system to tell the SSD, I'm not using these blocks anymore, even though you haven't seen any writes to them. Okay? So, like it says here, the file system can issue trim commands to the solid-state drive to say these blocks are no longer needed. So let's say that file F3 is deleted. Well, now the OS can say, hey, solid-state drive, I am no longer using these logical blocks. So you can stop babysitting them. Okay? So that's pretty crucial. And there was this constant issue pretty much with first-generation solid-state drives and OSs that didn't support trim, where access to the device would get slower, or I should say writes. Writes to the device would get slower and slower and slower and slower to the point where you had to basically reinitialize the drive. Erase everything. Okay? And then you could start over and it would be okay and it gets slower and slower. So now that everybody has trim, and trim is used really widely, we don't run into that issue. So that's the big deal with trim. Okay, let me see. Anything else? I don't really need to talk about this because that problem has been fixed. But and the other issue of not all OSs supporting trim, basically all OSs that are worth their salt do now. Pintos doesn't, but Pintos runs in a virtual machine in another virtual machine, so we're okay. All right, any questions? Okay, like I said, Wednesday we're not going to have class, just as a gift to you and to me, because I would love to go home before 1 o'clock and relax. And I'm sure you all would like to relax too. But next Monday, we'll have the file system design lecture. Next Wednesday, I'll talk about journaling file systems, which are really cool. And then Friday, we'll see if Bobby's willing to regale us with details of hypervisors. So that's the plan going forward. All right, we're done.